Hello everyone, welcome to our course Strengths and Stiffness of Beam Basic Principles of Steel Structure. Number 3.1.1 Strengths of Flexural Members. 3.1.2 Stiffness of Flexural Members. Now, let's look at introduction. Beams are widely used as structural elements in almost all kinds of buildings, bridges, and other engineering structures. Beams are used mainly for carrying transverse loads, which mainly generate moments and shears in a beam section. Axial forces can also exist in beams. However, it can be neglected when transverse loads dominate. Since beams are mainly used for carrying transverse loading, higher flexural stiffness and capacity are desirable. Now, first, bending strengths. As the material mechanics know, in the elastic stage, when the bending moment acting on the component section wraps around the spindle x-axis, the maximum positive stress at the edge of member section is expressed as the formula 3.1. Wnx is the net sectional modulus about x-axis. Mx is moments about x and y-axis. Now, here we can see the figure 3.1 shows the nominal stress distribution on the beam section in each load stage. When sigma reaches the steel yield point Fy, see figure B. Now, the member section is in the elastic limit state. As Mx further increases, the section of the member begins to develop plasticity inwards and enters the elasticoplastic stage, see figure C. Now, when the entire section of the member is completely plastic, the section reaches the maximum bending capacity, plastic bending moment. Then the section forms plastic hinge and reaches the plastic limit state. Now, Wp is the section plastic modulus of the section to the x-axis. Generally, gamma x and gamma y are plasticity factors or shape factors for x and y-axis. For each shapes, gamma x equals to 1.05. Gamma y equals to 1.20. For box sections, gamma x equals to gamma y equals to 1.05. For other shape, see table 3.1, which is show the plasticity adaptation factors. F is flexural desire strengths. You can see there are different factors around x and y-axis for different sections. The bending strengths of the beam shall be satisfied as formula 3.2. For beams bent in both directions, the strengths shall be satisfied as formula 3.3. My is moments about x and y-axis. Wny is net section modulus about y. Plasticity factors is not considered for beams requiring fatigue failure calculation. Gamma x equals 1. Gamma y also equals 1. Now let's look at shearing strengths. The shear strength is expressed as the formula 3.4. V is shear force of section. Ix is moment of initial of the gross section around the strength axis. S is area moment. Tw is web thickness. Fv is design value of shear strength of steel. When the member has shear force in both directions of principal axis is expressed as formula 3.5. At the same time, the checking conditions should be satisfied as formula 3.6. Let's look at local compressive stress as shown in figure 3.3, which shows local compressive stress distribution. There is no bearing stiffener at the concentrated load of the beam, or there is a moving concentrated load. The web of the beam will bear the local compressive stress generated by the concentrated load. the local compressive stress is greatest at the junction of the beam wipe and the upper flange and decreases to 0 at the lower flange as shown in Figure 3.3b. In fact, the local compressive stress is not uniformly distributed along the longitudinal direction of the beam. However, to simplify the calculation, assume that the local compressive stress is evenly distributed in the range of Lz. Now you can see sigma c is calculated as the formula 3.7. F is concentrated load. Consider dynamic coefficients for dynamic loads. P is concentrated load amplification factor. For crane beam, P adopts 1.35. For other beams, P adopts 1. For beam support, P also adopts 1. Lz is assumed distribution length of the concentrated load on the upper edge of the calculated height of the wipe, calculated as the follows. Now you can see concentrated load in mid-spine is expressed as a formula 3.8. At beam end, it can be calculated as the formula 3.9. A is the supporting length of the concentrated load along the span direction. The crane A equals to 15 millimeters. HY is the distance from the concentrated load to the edge of the calculated height of the wipe. HR is the height of the track. B is the distance from the beam end to the outer edge of the support plate. If B is greater than 2.5 HY, then take 2.5 HY. Now let's look at reduced stress. Shear and bending moments are generally acting on the beam at the same time. Sometimes local concentration forces are also acting. Although the normal stress and the shear stress are not maximum, it may be more dangerous under the simultaneous action of them. According to the 4-strength theory, in the complex stress state, if the reduced stress at a certain point reaches the yield point of steel in one-way tension, the point will enter the plastic state. So, the reduced stress is expressed as the formula 3.10. Sigma tau, sigma c are the normal stress, shear stress, and local compressive stress simultaneously generated at the same point on the calculated height edge of the wipe. They are expressed as the formula 3.11. In is net section moment of inertia. Y1 is distance from calculation point to neutral axis of beam. Beta 1 is increase coefficient of strength, design value. When sigma and sigma c are the same sign, take beta 1 as 1.2. When sigma and sigma c are opposite sign or sigma c is 0, take beta 1 as 1.1. Checking beam stiffness as formula 3.12. The stiffness of the beam is measured by the deflection under standard load. The insufficient rigidity of the beam will affect normal use or appearance. The vibration of the beam and dynamic influence can also be controlled by limiting the deformation of the beam. V is the maximum deflection in the beam caused by the standard value of the load without considering the partial factor and dynamic coefficient of the load. A lovable V is a lovable deflection value of B. That's all. Thank you for your attention. See you next time.